So, in the last couple of lectures what we were looking at was we tried to derive classification rules, classification functions, that is partitions of the sample space for two population problem. We had looked at various concepts like what happens to when we look at deriving a classification rule, when we have got say for example a rule which tries to minimize the total probability of misclassification. What type of rule do we get when we look at functions like expected cost of misclassification and the partition corresponding to one that would minimize an expected cost of misclassification. We had also seen in the last lecture for specific type of populations, namely normal populations, and we had seen how these optimum rules actually look like for these special type of cases of multivariate normal populations. So, the first thing that we are going to look at today will be performance measures of various classification functions. So, that gives us some way of comparing various partitions, various classification functions, and then we will move on to looking at classification problems in a multi-population problem. So, we will generalize whatever we have been doing for two population cases. We will look at generalizing that to a general C population problem. Let us start today looking at this performance measures. Thus, we are looking at performance measures for comparing different classifications. We are looking at comparing such different classification functions. Let us recall what we had defined earlier. We had a total probability of misclassification where we are considering still two population problem. So, that was given by P1. So, it is coming from first population getting misclassified into the second population, this plus P2 times P1 given 2. Now, this in terms of the regions that we have obtained. So, this is integration over the R2 region. The object is coming from the first population. So, it has got a density like this plus P2 into integral over R1, and since it is coming from the second population, it has got a density F2, this term, right. Now, based on this total probability of misclassification, we can look at the following measure, which is called the optimum error rate. Optimum error rate or OER. Now, that is what is corresponding to the total probability of misclassification rule, which minimizes that total probability of misclassification. So, this is what is corresponding to the minimum TPM rule. Now, suppose we have got this TPM minimum optimum TPM rule. Suppose that is given by this partition R1 optimum, R2 optimum. So, this gives us the minimum total probability of misclassification. Then this OPR expression is given by, or OER rather, is given by P1 into integral over R2 opt, this into F1x dx, this plus P2 times integral over this R1 opt region of the density for the second population F2x dx, right. So, this is one such measure for classification. You look at the optimum partitions that you obtain and then calculate what is the total probability of misclassification corresponding to that. Now, note that in this particular situation here, when we talk about R1 opt and R2 opt, these quantities, as we had seen in the earlier lectures, they depend on population quantities like unknown mean vector, unknown covariance matrix in case of multivariate normal populations, and hence for any practical purposes, given the data one based on the learning sample, one would be estimating these quantities, and the measure that is based on such quantities is what is called the actual error rate, actual error rate or AER. Now, this is given by the following expression. that instead of writing it as R1 opt and R2 opt, we write it as R2 opt cap, that is the estimate of that particular region based on the given sample data which is there in the learning sample. So, this is R1 opt hat f2x dx. So, this is a measure. Now, this R1 opt R2 opt caps and this R2 opt estimate are based on the learning sample which was denoted by L. So, these are based on the learning sample which is say script L, right. Now, once again if you look carefully at this OER or AER, although AER has got this estimate out here, we still keep it as f1x, f2x. So, these quantities are still unknown. Now, note that OER or AER, both of these depend on unknown quantities say for example P1, P2 and or as may be the case with OER or AER f1x, f2x, and hence they as such cannot be applied to compute for a given data what is the OER or AER corresponding to a partition rule. Now, a measure that is defined as an apparent error rate or APER. This is a measure that is going to be based on the sample data, and after the classification has been done, one actually would look at the proportion of misclassifications that is being done based on such a measure. Now, this is going to be defined as the fraction of observations in the training sample, because that is what we have in the training sample that are misclassified by the classification rule or the classification function. Now, how is that going to be defined? It is based on something which is called a confusion matrix. So, one first constructs the confusion matrix after the classification rule is put forward. So, one has got a first to start with the learning sample. Based on the learning sample the cases are pre-classified. Then based on those pre-classified cases one has constructed a classification rule. So, the sample classification rule is in place, and using the sample classification rule one has classified those pre-classified examples which were there in the learning sample, and then one looks at this matrix which is called the confusion matrix. It looks like the following. So, we will be having on one hand predicted class memberships. So, there can be two such predicted classes, pi 1 and pi 2, because we are still looking at two class problem, and each observation what we have has got another tag which is there in the learning sample. So, actual class membership. So, there are two possibilities, pi 1 and pi 2. Now, this confusion matrix based on the learning sample, that is script L, right. Now, suppose in this learning sample these are pre-classified examples, and hence after we use the classification function based on the sample data, when we are going to now classify the feature vectors, we are going to come up with some predicted class memberships. Now, these predicted class memberships are going to lead us to these numbers, say this is N1C, N1M. Now, this N1C is the number of observations coming from the first population pi 1 and being correctly classified by the classification rule. So, the predicted class membership is pi 1 corresponding to those observations coming from the first population. So, N1C is the number of correctly classified observations in the learning sample coming from the first population. Now, N1M is the number of observations that are coming from the first population. They are there in the learning sample, and by the classification function they are misclassified into this pi 2 population. So, this is this notation. Now, similarly we can define this as N2M. N2M is the number of observations which are actually belonging to the second population pi 2, and by the classification function are getting classified into the pi 1 population, and hence these numbers this number of observations N2M are wrongly classified examples coming from the second population. And similar to this one, we will have a number N2C here, which is the number of observations cases coming from the second population and also being classified to belong to the second population using our classification function. Now, the total cardinality of, suppose this L learning sample is N, then we will be having this, suppose, is the sum of these two numbers. So, this is N1C plus N1M. So, this N1 is the number of observations belonging to the first population in the learning set L, and this is N2, which is the number of observations belonging to the second population in the learning set, and this is the sum of N2C plus N2M. Now, if this is what we get as the confusion matrix, which is derived when we have a particular classification function in place, then these observations are misclassified coming from the first population, and these observations N2M are the number of observations misclassified coming from the second population. And hence, when we talk about apparent error rate APER, then it is a fraction of observations in the training sample that are misclassified by the classification function. So, this would imply that what we have, this APER, apparent error rate, is the fraction of misclassified observations. So, it is N1M plus N2M. These are the observations which are misclassified, that divided by N1 plus N2. So, this is in a perfectly implementable form. So, based on any classification function and the given learning sample L, one can compute this confusion matrix, and hence one can get to this apparent error rate. So, that can be computed for any practical data. So, we end this particular small section on looking at performance measures of for comparing classification functions. Now, we look at the important problem of extending what we were trying to learn in classification in terms of looking at a multi-class problem. So, let us look at that now. So, we are looking at classification under a multi-class setup. So, we make provision for more than two populations. Suppose we have got now C populations. Suppose pi 1, pi 2, pi C are C populations, C possible populations with prior probabilities of these populations, probabilities of these populations as, say, p pi 1, p pi 2, p pi c. So, the problem is simple, that we have got a multivariate normal, multivariate in general, not necessarily normal. We have a multivariate population, and wherein in the multivariate population there are C such possible populations. They may differ in their mean vector, they may differ in their covariance matrix or any other measure characterizing that particular population. And then these populations has got these prior probabilities p pi 1, p pi 2, p pi c, and given a multidimensional observation, we will have to look at in which class this is going to belong to. So, we are trying to classify a multivariate observation, a feature vector, into one of these C populations. Now, let us look at the three type of classification rules that one can think of. or the type of classification rules that we have derived for two population problem. Let us first look at the Bayes rule. Now, the Bayes rule is going to choose that particular population which has got the highest posterior probability. Now, let us write that we would like to assign a multivariate observation x to a particular pi, say pi j, if the posterior probability of pi j given this x is the maximum among all the possible populations. That is, what we are trying to do here is that let us denote by this quantity p pi j given x to be the posterior probability of the population pi j given x is observed. If this is greater than p pi k given x, if this is true for every k equal to 1 to up to c with k not equal to j, then we will assign x, the multivariate observation, to the population pi j, because the posterior probability of pi j given x, which is this, if that is the maximum among all possible such posterior probabilities for other populations. So, we have got a k which is not equal to k. So, this is basically what we have. Now, this can be written alternatively in the following form, that we have got using Bayes theorem. What we can write straight away is that probability of x given pi j, this into probability of pi j, this divided by summation j equal to 1 to up to c p x given pi j, these are multivariate observations, p pi j into this multiplied by p pi j. If that is greater than the corresponding quantity on the right hand side, so this is probability of x given pi k, this into the prior probability of pi k, that divided by summation j equal to 1 to up to c p x given pi j, this into the prior probability of the jth population. If that is true for every k equal to 1 to up to c with k not equal to j. So, we have got this to give us the Bayes rule, which looks at which population has got the maximum posterior probability given the observation x. So, this is in a nice form that we have got this to be the Bayes rule, wherein we can infer that this left hand side here, what we have is the posterior probability of pi j given x, and the right hand side is the posterior probability of pi k for k not equal to j for all other populations. Now, let us look at the total probability of misclassification approach, TPM minimizing classification rule. Now, how is that going to look like in this multi-class problem? The total probability of misclassification, the type of concept that we had introduced for the multi-class problem, this will take the following form, that it is summation I equal to 1 to up to c, then probability, the a priori probability of the pi I population into the probability of committing an error given an observation is coming from pi I. Let us see what are the terms here, because if we are looking at the term by term here. So, the first term is p pi 1 into the probability of classifying that observation which is coming from the first population pi 1 and then putting it into any other population. So, what is this probability of error, by the way? This probability of error given pi I, this is going to be given in terms of the partitions that we have. Suppose we say that let R1, R2, RC be the classification partition, That means that if x belongs to Ri, we are going to put it into population number I. That is, for every x that is belonging to this region, the class membership is pi 1. For every x that is belonging to R2, the class membership is going to be pi 2, and for the rest of these also. So, it is basically that. So, we can write this probability of error given an observation is coming from pi I here. So, that has got a probability which we had denoted earlier, Px given pi j. So, this is the density when we are looking at an observation coming from pi j. Now, this we are actually putting it into some other set here other than the ith set. So, this is I, x given pi I, and then this is integral over the complementary region of Ri, because if x belongs to Ri, then we are going to correctly classify it into pi I. Otherwise, if we are having x belonging to any other Ri not equal to that particular term for which we are looking at this, and hence this term can be written as omega minus this Ri. So, this is P x given pi I dx. Now, if this error is given by this particular expression, then this would imply that the total probability of misclassification for this multi-class problem expression is given by I equal to 1 to up to c p pi I into integral of omega minus Ri of p x given pi I, right. Now, let us see what this term is equal to. This term would be equal to this total probability of misclassification, thus is equal to summation I equal to 1 to up to c p pi I into integral over omega of p x given pi I dx, this minus integral over R I of p x given pi I this dx. Now, this expression is equal to 1. So, what we will be having is summation I equal to 1 to c p pi I. This is multiplied by 1 minus integral, we leave it as it is, the second term p x given pi I dx. So, the first term that we have here after we open the bracket is summation I equal to 1 to up to c p pi I, this minus summation I equal to 1 to up to c p pi I into integral R I p x given pi I to dx. Now, we note that what is this term equal to? The first term in this expression is equal to 1, because it looks at the prior probability, the sum of the prior probability of all possible C populations, and hence summation of this p pi I terms will be equal to 1. So, it is 1 minus this term here, that it is I equal to 1 to c summation p pi I into the term which we have there p x given pi I dx. So, this would imply that the rule, or rather minimizing the total probability of misclassification, is equivalent to maximizing this expression, which is the second expression. So, minimizing total probability of misclassification with respect to the partition R1, R2, Rc is equivalent to maximizing the quantity, which is summation I equal to 1 to up to c p pi I to integral over Ri Px given pi I dx, this with respect to the partition R1, R2, Rc. Now, the this partition that is going to lead us to minimum total probability of misclassification thus is same as the partition which would maximize the expression which is given by this, right. Now, what is that? So, the optimizing partition which is going to maximize this particular expression star is going to be that it is going to be the set of all x's for which we will have the corresponding term p pi I into p x given pi I to be the maximum. So, what we have here is finally that the maximization of star with respect to this Ri is obtained if on Ri we have the corresponding expression p pi I into p x given pi I to be the maximum. This is so because we are trying to maximize this particular quantity with respect to Ri. So, with respect to each of these Ri terms here, we are trying to find out p pi I into p x given pi I. If that is maximum, then the expression is going to be maximized. That is, allocation rule is going to be given by the following. Allocation rule is assign x to pi I if we have p pi I into p x given pi I is maximum for every I equal to 1 to up to c. That is, if we have got p pi I into p x given pi I to be greater than p pi k into p x given pi k. This is true for every k equal to 1 to up to c, where k is not equal to I, right. So, this is what is going to give us a partition, that is, we have got, in other words, Ri is the region of x's such that this term p pi I into p x given pi I is maximum over all I, overall overall I. So, that is basically what is going to lead us to this particular region, and hence if we have this as Ri, we can construct all the other regions. So, we will be having the optimum partition minimizing the total probability of misclassification. So, this would lead us to this R1 opt, R2 opt in the sense that it is leading us to the partition which is going to be the partition which would minimize the total probability of misclassification. Now, what we observe is the following, that when we have obtained this classification rule under the paradigm of say the total probability of misclassification, and we had earlier looked at the rule which was looking at the Bayes rule, which also was essentially the same. So, for a Bayes rule, what we had was this condition, this posterior probability to be greater than this posterior probability. However, we have got the both the denominators in the left hand side and the right hand side to be the same, and hence that is going to have the Bayes rule is going to be based on this expression being greater than the numerator of the right hand side, and hence the two rules are basically equivalent because we have got exactly the same rule here. So, this implies the total probability of misclassification minimizing partition or minimizing classification rule is same as the Bayes rule which maximizes the posterior probability. So, this is another justification of looking at either of these two rules. Now, next we are going to look at classification rule based on ECM, still on a multi-class problem. So, we will now look at classification rule or construction of the classification partition based on the expected cost of misclassification. Let us recall the structure. That is what we have. We have got pi 1, pi 2, pi c. These are the C populations, C possible populations into which an observation can belong to, and then we have got these as the prior probabilities. Say, let us write that is to be equal to p 1, p pi 2, say denote that to be p 2, and p pi c, which is the prior probability of the cth population given by p c. So, these are prior probabilities of the populations. The prior probabilities of the populations. We will also say that say for example, this the density of x, given pi I, say is given by fi x. This is for I equal to 1 to up to c. In our earlier notation, we had perhaps denoted this by px given pi I. So, that density we are denoting by fi x's. Now, we have got a multi-class problem, a C class problem. So, let us also look at the costs of misclassification structure, cost structure or cost of misclassification structure, cost of misclassification structure. We define that by CKI. So, this is the cost of misclassifying an observation, coming from the ith population, that is pi I, into the kth population, that is pi k. So, we have got this CKIs for I k equal to 1 to up to c. Now, we of course will be having this term with this CII, that is cost of misclassifying an observation, from the pi I into pi I. So, there is no misclassification as such, and hence we take this to be equal to 0. This is for every I equal to 1 to up to c, right. So, once we have this particular term in place, then we will look at constructing the region which is going to look at ECM minimizing rule, but before that we need to actually define how the ECM rule ECM looks like under the present situation. So, this is the type of partition that we are trying to get. So, this is the partition of this our classification. Then we can also have a similar notation as to what we had for a 2-class problem under a cost structure. So, this is what? This is the probability of, let me write that, this is the probability of an observation from pi I getting misclassified into pi k, getting misclassified into the population k, that is pi k. Now, what is this equal to? P k given I. So, this is going to be the integral over the region R k, because we are putting it into the kth population, wherein the observation as such is coming from the ith population. So, it has got a density f I x dx, right. So, we can also see what is p I equal to. So, this is equal to integral over the region R I f I x dx. So, that you can write this as omega, the full space, minus union of all other Ri's, this I, let me write this as k, this I is not equal to k. So, you are looking at the complementary region of Ri, that is omega minus union of all other regions which are other than I of this quantity f I x dx. So, this term, the first term would be integral over omega this of f I x dx, which is going to be equal to 1, and the next term is over union I not equal to k of these R k regions f I x dx. So, the first term here is going to be equal to 1, and the second term is summation over k equal to 1 to up to c with k not equal to I, because we have taken out that R I region from here, of these terms here integrals f I x dx. So, these are the quantities which would be required as such to define the expected cost of misclassification. Now, let us build up that expected cost of misclassification in the following way, that we first look at the conditional ECM, the conditional expected cost of misclassification of an observation x from pi 1 say to pi 2 or pi 3 or any of the other populations, that is pi 1, pi 2, pi 3, pi c, any of these is going to be given by say ECM 1. So, this is the conditional expected cost of misclassification of an observation x which is coming from pi 1 into any other population other than the first population pi 1. So, what is this going to be equal to? This is going to be equal to the probability, the cost, say first of all, suppose let us consider the case that x is misclassified into pi 2 given it is coming from pi 1. So, what is the cost of that? This is the cost that we are going to incur. From the general terminology, what we had said was pki to be this cki, the cost of misclassification structure. Cki is the cost of misclassifying an observation coming from pi I into pi k, and hence here we are looking at an observation coming from pi 1 and we are putting it into pi 2, and hence this is the cost that we are going to incur. And what is the probability of misclassifying an observation coming from the first population into the second? This is given by P21, where P21 is given by the expression that we have written for a general k situation here. So, P21 would in particular be integral over R2 of f1x dx. So, that is how this term is defined. This plus, suppose that observation is still from first and then it is classified into the third population. So, what we will be having is C3 given 1. These are all mutually exclusive cases. So, that we will be having this as the summation, the expected cost of misclassification. It is the conditional expected cost of misclassification given that it is from 1. So, that this would be given by this term, this plus the last term would be in this summation will be C given 1. So, this is the cth population. So, this is the cost of misclassifying an observation from the first population into the cth population, this multiplied by the probability of misclassifying this. So, this basically is equal to summation C I 1 into P I 1 summation of I from 2 to up to C. So, this is the ECM 1 term. Now, this ECM 1 is with a probability P 1. This ECM 1, so the expected cost of misclassification ECM 1 is with probability P 1, because that is the prior probability for the first population. So, if we have this conditional ECM of x from pi 1 getting misclassified into pi 2 or pi 3 or pi c to be given by this, the expression that we have written here with a probability P 1, because it is from the first population with a priori probability as P 1, we will have the expected cost of misclassification to be given by the expected cost of misclassification is ECM1, the conditional one, that with a probability P1, that times the expected cost of misclassification conditioned on the observation coming from the second population would similarly be ECM2 with a probability P2, and thus we will have to look at all such conditional probabilities, conditional cost of misclassification, expected cost of misclassifications, which is going to be given by this ECM C for the Cth population. So, we can write these terms without much of a difficulty, that this term would be equal to summation I equal to 2 to C, what we have written there, I given 1 into Pi given 1, this plus P2 would be a term. Now, what would be the type of terms that would be there in this conditional ECM of x from pi 2? That is going to be a similar sum with the sum, I will just write it as in the first term here, C I given 1 into P I given 1. This summation I is from 1 to up to C, wherein this C is not equal to 2, because we are looking at expected cost of misclassification, the conditional expected cost of misclassification of x from 2, and hence this would be the expression when we talk about ECM2, which is this expression. Now, in a similar manner we can write the other terms. So, the last term would be equal to summation I equal to 1 to up to C, not C, because C is going to be left out here. So, this is up to C minus 1 of the terms which are same as what we have in here. So, we can write this ECM under the present multi-class situation in the following compact form, that this ECM is equal to summation I equal to 1 to up to C, say, that is Pi times summation k equal to 1 to up to C, where k will not be equal to C of expressions which are Ck given I into Pk given I. That is basically the term that what we have out here. So, the summation is over I for this terms here, and then summation over k equal to 1 to C with k not equal to, I am sorry, k is not equal to I, because the outer sum here is I. So, if we have P1, then this sum k is not equal to 1. So, the summation here for p equal to 1 starts from k equal to 2. If we have I equal to 2, that is P2, we will be looking at summation over k equal to 1 to C without including k equal to 2. And similarly, for the last term, if we have here Pc, then this particular sum would run from k equal to 1 to up to C minus 1. So, in terms of the partitions that we are looking at, the classification partition which is R1, R2, Rc, minimizing the expected cost of misclassification, as given in this star 1 here, as given in star 1, is given by, we are now looking at regions, so that we will be allocating x to a particular population pi k. There are C such possible populations, k equal to 1 to C, for which we will be having the inner sum here, that I equal to 1 to C, say, with I not equal to k, because we are looking at this pi k, for which we will be having this Pi into fi x c k given I is smallest. Why is that so? Because this particular term, if you recall, that pki is in terms of this, and hence this expected cost of misclassification, I will just write this expression which should lead one to get to this particular term here, which is summation I equal to 1 to c. So, this is that star 1 expression which is equal to I equal to 1 to c. I will take this pi also inside and write this expression as k equal to 1 to up to c with k not equal to I. So, we will have a pi, let me also take it inside. So, we will have an integral here r k f I x dx. So, rather than writing it in this form, I will also take this constants inside the integral. I will write it as pi into c k given I, this into f I x dx. So, this is an alternate expression of star 1 in terms of breaking up this particular term here pki, because this pki here, as we have noted earlier, this is integral over the region r k of f I x dx, and hence this star 1 expression is going to be given by this. Now, if we are now looking at the rule, the partition r 1 r 2 r c of the sample space, which would lead us to minimizing this particular expression, we will look at choosing that particular region r k such that we will have this term here, which is given here, to be the smallest among all possible k's, and hence this is what is leading us to the region r k, that is r k is the region of all x's such that we have got this summation that we had written in the previous slide, that I equal to 1 to c I not equal to k of pi f I x into c k I to be the smallest, right. That is, the expression here which we have is going to be less than the expression for every other k other than the region wherein we have got this k here. So, that is summation I equal to, this is the left hand side only, this is I equal to 1 to up to c with I not equal to k of the expression pi f I x c k given I. If that is less than summation over I equal to 1 to up to c I not equal to j. So, you take out some other term in this sum here, and that would be pi f I x c k I. This is for every j equal to 1 to up to c, and j is not equal to k. So, we will be looking at all such sums, deleting a particular I index I equal to 1 to c, and the region r k is going to be the region of all such x's for which this left hand side is less than the right hand side out here. So, this is what is giving us the rule which minimizes the expected cost of misclassification, and the allocation rule is what we have written here, that to allocate x to pi k, if we have got the summation here to be the smallest among all possible such k terms. Now, we will note that this particular rule here under the equal cost setup, the above classification partition reduces to what? if we look at this particular partition here, it's that we are going to have this to be smallest. Now, if all the costs of misclassification are same, that is under the equal cost setup, these costs of misclassification is not going to play any role. So, this can be taken outside. So, if we have got equal cost setup, the this partition here is going to be reduced to allocating x to pi k if we have the summation I equal to 1 to c I not equal to k pi if I x is the smallest among all such c summations for which we will be having this I not equal to that particular chosen index there. So, this is what we are going to get if we assume that we have got equal cost structure. Now, when is this going to be smallest? If the term among all the c terms I equal to 1 to c that is taken out is the largest. That is, if we have got the term which is taken out. Now, what is the term which is taken out if we are looking at I equal to 1 to c? It is the term corresponding to k. That is, if we have got pk times f kx to be the maximum. So, if we have got to be the maximum, we are essentially looking at this rule that we are going to allocate x to pi k if we have got, I said that this pk fk is the maximum. That is, if you have f pk times fkx, this is greater than pj times fjx for every j equal to 1 to up to c with the j not equal to k. So, we are not looking at that kth product on the right hand side, we are looking at all other c minus 1 products, and hence we are looking at this all these c terms and then finding out for which of those c possible products we have got the product to be maximum, and then x is going to be assigned to pi k corresponding to the population for which this is going to be the maximum. Now, recall that when we were looking at the total probability of misclassification rule, what was the rule that we had got? Let us look back and see what we had got earlier. When we were looking at the total probability of misclassification rule, we had said that the total probability of misclassification rule is 1, that is going to assign x to pi I if the probability product here like this is greater than this type of probability product for all other products other than I. So, this essentially in terms of our notation, we have in the present case denoted this to be equal to pi and we have denoted this to be fi. So, what we were trying to say is that in total probability of misclassification minimizing rule, that x is going to be allotted to pi I if pi fi x is the maximum over all possible such i's I equal to 1 to c, leaving out that particular I which is on the left hand side. Now, if we look at the expected cost of misclassification minimizing rule which we have derived just now, which was this, and that under an equal cost setup was reduced to allocating x to pi k if the sum like this is the smallest, or in other words the term which is left out in this particular sum here is the largest, that is x was being allocated to pi k if the pk fkx is maximum among all possible such products. So, this would imply that under the equal cost setup, we can just remove this bracket actually, under the equal cost setup, this would imply that under the equal cost setup, the ECM minimizing rule is same as that of the TPM minimizing rule. So, this ECM minimizing rule is same as the TPM minimizing rule. Well, this is what we expect also, because if we consider in the ECM setup, there is nothing special about the ECM minimization, or rather any special structure of the cost is not assumed, then the rule which would minimize the ECM would naturally be same as the rule which would minimize the total probability of misclassification. And hence we have also seen that that is what is happening, that if we take in the ECM minimizing rule the cost structures to be identical without having any special preference about the misclassification costs, then the total probability of misclassification rule can be derived from the ECM minimizing rule. So, we will stop at this particular point in this lecture. In the next lecture, we will first look at some examples of how to apply for a multi-class problem this type of concepts of ECM minimizing rule or TPM minimizing rule, and then we will talk about some other important concepts in this classification problem. Thank you.